Section 4.1 is about polynomial functions. First of all, let's take a look at some prerequisite skills that you had in algebra and probably reviewed a little bit in algebra 2. And again, we're going to need them in pre-calculus. So let's go ahead and talk through some of these things and refresh your memory on some of these things. The first one here says factor x to the fourth minus 81. If you would remember what a difference of perfect squares is, remember we're doing what's called factoring. Also, some of you guys know it as reverse foiling. But we need to get this equation to look like it did before we foiled it out. So what this actually is it's called the difference of perfect squares, if you remember that. And this guy's a perfect square. The square root of x to the fourth is x squared. And the difference of perfect squares means we're going to break it into two parentheses. And if I were to FOIL these out again, it would be this exact thing right here. So the square root of that is x to the fourth, and then the square root of 81 is 9. So the difference of perfect squares is going to break down into x squared plus 9 and x squared minus 9. All right. We're still not done yet. When it has a plus sign, it's not the difference of squares. In fact, it just remains the same and it stays there. That's in factored form. However, when we have a perfect square minus a perfect square, hence the name difference of perfect squares, we have to break this down farther. X squared is a perfect square because I can take x times x and get x squared. So the square root of x squared is x and x, and then since it's a difference of perfect squares, it's going to follow the same pattern of plus and minus. And the square root of 9 is 3. And then again, we go ahead and just drop this down because that guy is in factored form, x squared plus 9. So that's how you would factor number 1 there. Number 2 is a reminder of a trinomial when we just have 1 as a leading coefficient. And I can show you another way here in 1 and 4 are very similar. Let's show you 1. What we need to figure out is what multiplies to be a negative 16 and adds up to be 6. And how I like to describe it to my algebra kids is that this sign tells us whether the sign is the same or it's different. So if this was a plus sign, it means the two signs are the same because a negative times a negative is a positive and a negative times a positive is a negative. So if this sign is negative, we're going to have two different signs in our parentheses. So we're going to have to break it down into x times something and x something like this. All right. This sign, this negative sign means it's going to be different. So one's going to be a plus and one's going to be a minus. And the plus sign here tells me that the bigger one is negative. All right. So I need to figure out what multiplies to be 16. Well, I know 4 and 4 does, but that doesn't add up to be 6. I know 2 and 8 does. And if I make the bigger one positive, that's going to add up to be 6. So it's going to be a plus 8 and a minus 2. And that is that guy factored. If I were to FOIL this back out, I'd get x squared minus 2x plus 8x minus 16. And that would get me then a 6 here and obviously negative 16. What I meant by the same sign, if say this was x squared plus 8x plus 16, this means that the signs are the same. So my parentheses then would break down into x plus and x plus because this sign tells me that they're both positive signs. So x plus, then we need to figure out what multiplies to be 16 and adds up to be 8. Well, we know that is 4 and 4. So that's what that means by plus sign. If we had something that was like x squared minus 8x plus 16, this sign means that they're the same. This sign means that they're both negative. So it'd be x minus, x minus. And we know that then 4 times 4 is 16, so a minus 4 and a minus 4. And the reason we get that work to be a plus sign over here is because negative, when we FOIL that out, negative 4 times negative 4 is a positive 16. So that's why that rule works. And again, if it was the opposite here, maybe instead it was x squared minus 6x minus 16. This tells me that the bigger one is negative. The signs are different. The bigger one is negative. So this would break down into a x, and it would break down into an x out here. They're going to be plus and minus, but the bigger one's going to be negative. So in this case, a negative 8 and a positive 2 would multiply to be a negative 16 and add up to be negative 6. So it'd be minus 8 and plus 2. All right, so hopefully that wasn't a big overhaul for how you factored. I don't think it will be. I think this should be a pretty big review. In number 3, the first thing you always look for, what you can do is if you can take a common term out. These first two just so happened that I couldn't take a common term out. I just kind of skipped over that step, but this one jogged my memory. First thing you always look for is whether you can take a common term out, and these guys all share an x. So the first thing I'm going to do is I'm going to take an x out of each of those guys. So on the outside I have x times x squared plus 3x minus 4. And then again, I can factor what's inside this parentheses now. This sign out here means that my two signs are going to be opposite. And this sign up here means that the bigger one is going to be positive, so it's going to be x plus and x minus because of this first sign, or the last sign. The bigger one's going to be positive. What multiplies to be 4 and adds up to be 3 is a positive 4 and a negative 1. And again, we'll have the x to the outside. All right. And then number 4, this now we have a coefficient of bigger than 1 out in front. Maybe makes it a little more complicated, but not necessarily. So all we have to do in this one now is that since it has a number bigger than 1 up here, we're going to change it slightly. And actually, you can do this way even if this is a 1. We could do the same method even up here. But what we have to figure out is what multiplies to be this number times this number. So what multiplies to be 60, and it's going to have to add up to be this middle number, negative 11. Well, again, read the signs. The signs mean that one's going to be positive, one's going to be negative, and this is saying that the bigger one is going to be negative. So let's think of things that multiply to be 60. Well, I know 2 and 30, and I know 3 and 10. And I know 4 and 15, and I know, why did I say 3 and 10? 6 and 10, my bad. 3 and 20. But anyway, we know that the bigger one is negative, the smaller one is positive. That's why I listed them in this order. And which one out of these, which one adds up to be 11? If this is a negative 15 and a positive 4, that's going to be negative 11. So all we do to finish this problem is we rewrite this. And what we're going to do is we're going to replace this negative 11 with a negative 15y plus 4y. And that's all we're going to replace. We're going to rewrite everything else the same. We're just going to replace it. So I'm going to have 6x squared minus 15y, and it doesn't matter what order you put this in, plus 4y minus 10. And it doesn't matter what order you put this 15y and this plus 4y, it has no bearing, it doesn't matter. The next step, and what we're going to do is we're going to group it. We now have 4 terms, and that was the point. We are expanding it out so we can now group it. And what I'm going to look for is what common term can I take out of this. Oh, they're all, sorry, they shouldn't have been y. They should have been x's, my bad. I don't know when I got the y's. They're x's. My bad, you just replace this. Now, would you agree that negative 15x plus 4x is negative 11x? Sorry if that y confused you. But now we're going to group it, see if we can pull out a common term. Here I'm going to pull out a 3x. And when I pull that 3x out, this becomes 2x, and this becomes minus 5. And what can I pull out of here? Well, I can pull a 2 out of here, so I'm going to pull a positive 2. And this becomes 2x minus 5. And the key to this is you have to pull out the number here that's going to make these two guys be the same. Since these two are the same, we can pull the 2x minus 5 out of the equation and write that in a parentheses, and then we can rewrite what's left in a parentheses, so 3x plus 2. There's other ways to FOIL that, or to factor that. You can think of the factors of 6, and you can play around, do some guessing and checking. You can 6 and 1, you can have 2 and 3. I like this way much better because it eliminates the guessing and checking. So this is the way I factor. Anyway, so that's a little prerequisite skills for what we're going to do today. What we're going to talk about today is polynomials, and you've talked about them before in your math career, but they all have one variable. Their coefficients are complex numbers, which mean they can be real or imaginary. Imaginary numbers are ones with i's in them. And then the degrees have to be bigger than 0, so no negative degrees. So are these polynomials? Name the leading coefficient and the degree of the polynomial if they are. Looks like number 1 is not a polynomial because it has to be one variable. So that actually 2 variable, not a polynomial. This one all has one variable. The degrees are bigger than 0. They're all positive. This is a polynomial check mark. And then it wants its leading coefficient. The leading coefficient we haven't talked about is the number that's in front of the biggest power of w. The biggest power of w in this case is w to the fifth power. W to the fifth power is bigger than w to the fourth and bigger than w to the third and so forth. So this guy's leading coefficient then is positive 5. So the leading coefficient is positive 5. And then C, asking if it's a polynomial. This is not a polynomial. It does have all one variable. However, I can rewrite this 3 divided by x, and I can bring that x to the top. So 3x squared plus 3x to the negative 1. That would mean it would move from the bottom to the top, plus 8. This power is not bigger than 0. It's actually less than 0. Therefore, that is not a polynomial. Moving on to what we really want to get into in this section is talking about a root. Well, a root is a solution to a polynomial, and it's where that polynomial equals 0. So anytime we say we have a root of a polynomial, it means where it's a 0. And when you find out later, it's when we're going to have an x-intercept. That's what a root is an x-intercept, where the polynomial equals 0. So they're asking us to determine whether 3 is a root of this equation right here. So all we need to do is plug in 3 into our equation and see if that gets us to 0. If it gets us to 0, it's a root. If it doesn't, it's not a root. All right, so if I plug in 3 in here, 3 cubed is 27 minus 3 squared is 9 times 2 is 18 minus 15 plus 6 equals 0. So I think I got all those right. 9 times 2 is 18. Yeah, 20. Yeah, it's 27, 15. All right, so add these together here. I get 27 minus 18 is 13, right? Minus 15 plus 6. That is not going to equal 0. So therefore, 3 is not a root of that of this equation here. They're asking us to determine whether negative 3 is a root of this other equation here. So negative 3 would be negative 27 plus negative 3 squared is 9 times 3 is 27. And then minus, then negative 3 times negative 3 is positive 9 plus 6. And that these guys go to 0. And 9 plus 6 is 15. So actually, neither of these guys are roots. It's not a root of either one of those. So it'd have to equal 0 in order for them to be a root. And in this case, neither of them were. A root can be an imaginary number of a polynomial, but it can be imaginary, but obviously we can never graph an imaginary number. So a root might be an imaginary number, and it might be an actual real number that we can graph. The fundamental theorem of algebra says that every polynomial equation with a degree greater than 0 has at least one root in the set of complex numbers. So we're always going to have a root. We'll always be able to solve for the root of a polynomial. All right, and it's either going to be a real number that we can graph or an imaginary number with I, like the square root of a negative number. That's an imaginary number. A corollary to the fundamental theorem of algebra says a polynomial equation of a degree n has exactly n complex roots. What that is saying is if my leading degree, so if I have an x to the fifth equation, plus 2x or whatever it is, it's going to have 5 roots. All right, it's going to have 5 complex roots. They might be, 3 of them might be imaginary, 2 of them might be real, 5 of them might be imaginary, and 0 might be real. It's going to be a combination of real and imaginary numbers. All right. So this next paragraph here is kind of explaining, it's kind of thinking through that corollary a little bit more. It says an even graph does not have to cross the x-axis. Notice this is an even graph right here. It's a parabola, right? Does not have to cross the x-axis. It's like graphing y equals x squared plus 1, and we moved it up 1. All right? So an even graph will not have to cross the x-axis. Therefore, it won't always have a real root. But an odd will have to. The odd graphs are always the disco dancer graphs, like x to the cube. It's always going to cross that. So something to the odd power will always have at least one root, at least one real root. All right, but the graph of an even one doesn't have to. All right, so And if you think about it, if we had a graph x squared plus 1, and we wanted to solve for the roots of that when it equals 0, if I subtracted 1, x squared equals -1, the square root of that. So I have imaginary roots here. All right, so that's an example of something that's not going to have a real root, but imaginary. That's why it doesn't cross the x-axis anywhere in there. Okay, so it does not have to cross, and even does not have to, and odd does have to. It'll have to at least once, maybe more. Example 3, state the number of complex roots and then find them. Well, this polynomial here is a third degree polynomial. It'll have 3 roots, and we'll have to find how many of them are complex and how many of them are real. We know that at least one of them is going to be real because it's going to have to cross the x-axis one time because that's the shape of its graph. So in order to solve for this guy, we're going to have to factor it out to solve. So we're going to take an x out of all these guys. So if I take an x out of all of them, I get x squared plus 2x minus 8 equals 0. And again, we're going to have to factor this guy farther. We'll have to think what multiplies to be -8, adds up to be a +2. I'm going to keep my x to the outside. If I break this down into my 2 parentheses, because I'm factoring it farther, x and x, this sign tells me that they're different. Bigger one's positive. So what multiplies to be 8? 2 and 4 multiply to be 8. If I make 4 the positive one and 2 the negative one, that adds up to be a +2. And to find my roots again now, all we have to do is set each and every parentheses or something outside the parentheses being multiplied equal to 0. Because if I make this guy equal to 0, if I make him equal to 0, 0 times anything is 0. If I make this guy equal 0, 0 times anything is 0. If I make this parentheses equal 0, then 0 times anything is 0. So we set each of these equal to 0. X equals 0, x plus 4 equals 0, and x minus 2 equals 0, and solve. So our roots are going to be at 0. It's going to be at -4, and we're going to be at 2. So in this case, that graph is going to come and touch that x-axis at 3 points at 0, -4, and 2. I'm going to go ahead and let you do B on your own in your notes. And if you have an imaginary, just write it like maybe you're taking the square root of -15, all right? Just say the square root of -15 or root 15i, right? So that would indicate a negative root, okay? That's an imaginary number. You guys went over those in Algebra 2, I believe. Last example I have for you, and then I'm going to let you try one in your notes. It says write a polynomial equation of least degree with roots, so forth. So they give us 2 imaginary roots. And if you think about that last equation that we had, when we factored it out, we were at 0 and we were at like x equals 3, and I can't remember exactly, and x equals 1, right? The step before this would be that x minus 1 equals 0, x minus 3 equals 0, and then we just had something times x in this case for 0. But that was a step before, so we're going to work backwards. So we know my root is -3, so before my answer, I would have had to have x plus 3, because if I set this parentheses equal to 0, that would have gotten me a -3. And then in this case, I know I would have had to have a x minus 2y, and then I have to have an x plus 2y if I were solving. And I'll get to these i's things. Those are imaginary roots, but I'll get to what that means here in a second. Let's go ahead and let's FOIL this thing with the i's in there, and I'll show you why here. That's actually a difference of perfect squares. When I FOIL that thing out, I get x squared minus 4i squared. And the reason I did that, if you think that I equals the square root of -1, right? So if I take the square of both, if I have a square of both sides, I squared equals -1. So instead of I squared being here, if I plug -1 into here for I squared, then I have -4 times -1, which is +4. So I have x plus 3 times x squared plus 4. And in order to write my polynomial of least degree, all I need to do is FOIL this out. So I have x cubed plus 4x plus 3x squared plus 12. And if I wanted to, I can rewrite it in descending order. X cubed plus 3x squared plus 4x plus 12. And that would be my in least degree, my polynomial in the least degree. So if that I part confused you, go ahead and rewatch it, but it should make sense that if I equals the square root of -1, if we square both sides, it gets rid of the square root sign, so I squared equals -1, and all I did is I substituted that in right here where I saw negative or an I squared, and I made this -1 and multiplied these two guys and got a +4. And that makes sense. If I set x squared plus 4 equal to 0, subtract 4 over, I have x squared equals -2. If I take the square root, I get x equals the square root of -2, which is the same thing as x equals -2i. So that makes sense. I hope this makes sense to you. What I want you to do is I want you to try this one on your own, and we'll talk about it in class. And we'll hope this helps. We'll see you in class.